d theta, so what we wind up with is we have 1, 2, 3, 4, 5 factors of 2. So computer science majors, quick, what is that? 2 to the fifth? Yes, okay. Oh, yeah, you can be extra quick with powers of 2, more than normal people. So, all right. Okay. Cosine to the 4th. Now, so yeah, as you can see, this thing is pretty nasty. So what you'd have to do in order to try to figure this out is, well, cosine squared theta is 1 plus cosine 2 theta over 2, and then you could so then you'd have this squared. So then you can expand that out. You get some cosine squares in there, because cosine squared or sine squared just by itself is something that's kind of a pain to do. So as you can see, I mean, even well before we got to that point, it already got ugly as soon as we had to do this. And now, now it's just this much worse by the time we do all this expanding and so forth. Eventually you get to the point where you can integrate all this directly, and then what you need to do is put everything back in terms of x. So wherever you see a sine x, or sine theta, you replace it with x over 2. Wherever you see a cosine theta, it's this radical over 2, and so forth. So it's definitely not very pleasant. So leaving in terms of x, y, z, maybe not the best idea. So instead, if we work in terms of cylindrical coordinates, our z is not going to change. It extends from x squared plus y squared all the way up to 4. So that our innermost integral is not going to change. But if we look at the top of a solid in terms of x and y, and we have x squared plus y squared is equal to 4, then how do we integrate over a region like this? By converting basically to polar coordinates. That's what cylindrical is going to involve. Where would that put us? What would be our limits in terms of r and theta? If we wanted to integrate over this portion of a circle, now keep in mind y, this is a y-axis right here. So keep that in mind for computing your limits in terms of theta. So what will be the limits in r? Now, since r is equal to the square root of x squared plus y squared, yeah, so r would run from 0 to 2. All right, and then for this portion of the circle, now keep in mind I've turned things 90 degrees just because it's consistent with the view of a solid that I erased. So here, if you want, you can turn this way and look at it, if that'll help you figure out what the limit should be.
0 to pi?
Yeah, 0 to pi.
It did help.
It did? Oh.
Yeah.
Okay. All right. Nobody send chiropractor bills, please. All right. Now, in terms of cylindrical coordinates, we have 1, and then don't forget the factor of r, just like we had in polar coordinates or double integrals. So now our limits in terms of z are x squared plus y squared to 4, but x squared plus y squared, that's r squared. So we have r squared to 4. And then in terms of theta, it's 0 to pi. In terms of r, it's 0 to 2. So now our limits are a whole lot simpler than they were before. So now this is something we can actually integrate. No trig substitutions required. All right. So here we have this factor of r, but we don't need it now because we're integrating with respect to z and then theta. So we can copy the r, or not copy it, we're cutting and pasting. So we'll stick the r out here. Then we have 0 to pi and theta, and then 1 dz, d theta dr. So now we're going to get 4 minus r squared. 4 minus r squared d theta dr. And now we're going to integrate that with respect to theta, but all that's going to do is multiply this whole thing by pi, because this is independent of theta. So finally, all right, we have an r out here. So now we're going to have 4r minus r cubed dr. So that's it. Definitely a whole lot easier than using a trig substitution. So we're going to get pi 2r squared minus r to the 4th over 4 evaluated at 0 and 2. So what we end up getting once you plug and chug is 4 pi. I'm reminded of one of my colleagues, Dr. Kollewall. What he likes to do on an exam is give a problem where if something like this occurs to you, like to convert to cylindrical coordinates when it's warranted, then the problem actually is fairly straightforward. If you don't think of that, you could still do a problem, maybe using a method such as this, but it's going to take a long time. Now, that's how he works. I'm not saying it's necessarily how I would work, or at least not to the degree that he does, but my point is, it's well worth the time to try to come up with what is the best approach possible for a problem at hand. And because I've often said, because I've found this to be absolutely true, a difficult math problem is an easier problem that's being looked at the wrong way. Notice I said easier, not necessarily easy. Quite useful for spherical coordinates. So this is a more interesting generalization of polar coordinates to 3D. So spherical coordinates, we have rho, which plays the role of r. We have theta, which is similar to the theta you're accustomed to for polar and cylindrical. And another angle, phi. So the meaning of these, you have your sphere. Okay, so rho is the radius of the sphere. So rho is equal to x squared plus y squared plus z squared. What about these other angles, theta and phi? So theta is an angle that's just for x and y, nothing to do with z. So it has the same meaning as in polar coordinates. So if we have a point out here somewhere on the sphere, it sweeps out an angle, theta, within the xy plane. It's that angle, but it's the same interpretation as in polar coordinates. So theta goes between 0 and 2 pi. So that's the purpose of theta, is to indicate where in the xy plane the point is in terms of an angle. But we also need to specify elevation or inclination, if you will. So you can think of theta as representing longitude. You need the other angle, phi, to represent latitude. Now phi runs between 0 and pi. Draw another diagram that'll give you ideas to how to interpret phi. So now if we take this sphere and we look at it from the side. So here's some point on the sphere. So we have this distance, rho. Now this distance over here, this would be the square root of x squared plus y squared. So we're looking at an appropriate a plane corresponding to theta. And then this distance, that's z. Now, phi is actually this angle here. So phi is an angle of inclination. Now, when phi is equal to 0, you're at the North Pole. And when phi is equal to pi over 2, that's the equator. And phi is equal to pi, that's the South Pole. So phi sweeps from North Pole to South Pole. Now, we'd like to be able to relate x, y, and z to these spherical coordinates. So your distance, your latitude, your longitude. So if this is our angle phi, then, so what's this angle going to be? How much is this right here?
It's going to be 90 minus whatever the measure of phi is.
Yeah, so it's going to be pi over 2 minus phi. And this angle? Yeah, so 90 minus this. That just gives you phi again. So phi's over here. All right. So now, if we know rho and we know phi, what is z? Cosine. Z is v adjacent. So cosine phi is adjacent over hypotenuse. So therefore z itself is rho cosine phi. All right. So we have one Cartesian coordinate taken care of. We know what z is in terms of the spherical coordinates. So we want to nail down x and y. Okay.